Looks like everyone got this right. That's right. Imagine a place in the cosmos far from all gravitational and frictional forces. Suppose that you visit that place. Of course, suppose I'm not asking you to go there. And throw a rock. What will the rock do? Okay, Colin, now's the learning part. Now's the listening to me part. Yeah. The rock will continue motion in the same direction at constant speed. Everybody knows that, right? Objects in motion stay in motion. Constant speed, straight line. Okay. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at this speed in the same direction? The same question. Objects in motion stay in motion. How much force do you need? The answer is a big fat 0. Objects in motion stay in motion. You guys all got that in question 1. How is it different? Because there's numbers?
Yeah. Basically.
How much net force is required? Objects in motion stay in motion. Now, does it take a force to keep something moving? Remember? Like if I kick this, right? How come? Because of friction. But the question doesn't say that. It says how much net force, total force. Right? So if there's like 10 newtons of friction, I need to push with 10 newtons. Okay? Taryn, I'm still teaching here, you realize, eh?
Yeah.
Okay. Got it. Okay, so Mac and Tosh, good write that, are arguing in the cafeteria. Mac says that if he flings the jello with a greater speed, we'll have a greater inertia. Tosh argues that inertia does not depend upon speed, but rather upon mass. And who do you agree with and explain why? And the correct answer is, drum roll please, correct answer is B, Tosh. Inertia is only mass. Inertia is the object's need or innate quality. It's desire to continue doing what it's doing, right? When there is inertia in motion, that's called momentum. Inertia in motion is called momentum. And that's actually the unit we're on in grade 12 right now. Inertia in motion is called momentum. Suppose you're in space in a weightless environment. Would it require force to set an object in motion? Remember, objects in motion stay in motion. Objects at rest stay at rest. And so the correct answer is yes. Right? If you want to accelerate it, even though there's no gravity and no friction on that, right? If you want to get something moving, you still have to push it. Okay? So yes. Would it require force to keep it in motion? No. So that's different, right? This is to set it in motion. What is your question, Paul? Is there a gravitational field around asteroids? It depends on their mass. If they have to be reasonably massive to have space, well, commonly misunderstood. Emily, you should be listening more, not talking to this guy. That's when you miss out on things that are important on tests. What was Colin asking? Something about an asteroid. And what was my answer? Oh, good guess, yeah. I mean, everything's got gravity. Colin, you've got a gravitational field around you. It's just that it's not very big, right? And asteroids are bigger than you. So, yes, asteroids have gravity. Is it enough to attract other things? No. If you landed on an asteroid, contrary to, what's his name there? The guy who looks like me. It's Bruce Willis. There's a picture of me. Oh, no, it's Vin Diesel looks like me. You know the movie where I think it's Ben Affleck and Bruce Willis land on the asteroid and they're drilling, they're going to bust it up. Armageddon, that's what it's called, yes, right? Yeah. Yeah, probably not enough gravity for you to sort of stand up. Okay, Fred, you know Fred. spends most Sunday afternoons at rest on the sofa watching pro football games, consuming large quantities of food. What effect, if any, does this practice have upon his inertia? Well, it increases. Right? If he's eating lots of food and not being very active, he's going to increase his mass. It's going to slowly, over time, increase his inertia. Go ahead. Would I be able to push it? Well, okay, so let's say that I am Bruce Willis and I'm landed on the asteroid, and I'm like, how would I push it? Like, I would just kind of get on my hands and knees and kind of
You'd have to jump off.
You're floating in the shuttle,
No, outside.
outside the shuttle.
Here's the rock. Here's the like that.
Well, I mean, aren't you on the surface of the rock then? How would you touch it then?
You just push it.
Then you're on it. You can't be like you're beside it.
It's like if you push that wall.
Like
You're
this.
not on, but you're not standing on the wall.
Okay.
Pushing it.
Okay.
Okay.
So
You just push yourself.
so here's this big rock,
Yeah.
and here I am, right there, floating, and I reach out with my 47-foot arm and I push it.
You can't.
Do you
I
have
don't know. Do you push yourself further? Maybe like outside of this room.
Oh, okay. Okay. So could you push it? Sure. You know what would happen? You go back.
But would it?
Absolutely.
but like
Yeah, not that much, right? It would already be moving, wouldn't it? It's not just floating, right? It's already moving. Nothing in space just sort of hangs there. Nothing in space just hangs there. Okay. Ben Too Close is being chased through the woods by a bull moose, which he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating. But if Ben makes a zigzag pattern through the woods, he'll be able to use the large mass of the moose to his own advantage. Explain this in terms of inertia and Newton's first law of motion. So, the moose has more mass, so he has less inertia. He is not able to make zigzags as easy. The moose has more mass, so he has more inertia, so he's not able to make zigzags as easy, or it will not work. The moose is still able to make a zigzag pattern. Correct answer? Correct. B. The moose has way more mass, okay, and he's not able to sort of, do that back and forth kind of thing, right? Not able to accelerate, change direction easy. No. Mooses can run fast in a straight line. Much like a running back in football, right? Goes back and forth. The larger linemen and the linebackers don't have that same lateral quickness. They can't go side to side as fast. The Titanic is another good example. Saw the iceberg, couldn't turn. How come? Giant. In fact, you could say that it was Titanic. Two bricks are resting on the edge of his lab table. Shirley, she's short, stands on her toes and spots the two bricks. She inquires an intense desire to know which of the two bricks are most massive. Since Shirley is vertically challenged, short, she is unable to reach high enough to lift the bricks. She can, however, reach high enough to give the bricks a push. Discuss how the process of pushing the bricks will allow Shirley to determine which of the two bricks is most massive. What difference will Shirley observe, and how can this observation lead to the necessary conclusion? So, the brick that moves more has more inertia and is heavier. The brick that moves more has less inertia and is lighter. Or, sorry, I guess this should actually be, these should really be, does yours say more massive? What does your sheet say? That should really say more massive and less massive. I prefer that. Both bricks feel the same, move the same distance. So what's happening? What's the correct answer? Correct answer is B, yes. And overwhelmingly you guys said B, so that's good, right? The one that moves more has less inertia, less massive. Really light things, right? Like this little wooden doorstop, right, is much less massive. It goes a long way. Heavier things like the scale with the same amount of push, hardly go at all. It's not rocket science. Well, maybe it is. Okay. Here's where it starts to get tricky. Listen carefully. What's the kid's name, first of all?
Luke.
Out below. Look out below.
Look out.
Oh my goodness, that's me.
That's awesome.
Thanks, Riley. 100%. Riley, you don't even have to break this down.
Thank you.
Look out below drops an approximately 5 kilogram fat cat of approximate weight 50 newtons off the roof of his house in the swimming pool below. Now, before I begin, before I go any farther, this is a fictional cat. No actual cats were harmed in the making of this question. Okay? Upon encountering the pool, the cat encounters a 50 Newton upward resistance force, assumed to be constant. So 50 newtons of gravity, 50 newtons of buoyant force up. Use the description to answer the following questions. Which one of the velocity time graphs best describes the motion of the cat? There's the cat right there. He's pretty fat. Support your answer with sound reasoning. Is it A, B, or C? And the correct answer is B. Why is it B? Okay, well, let's talk about this. So, here's the cat, right? And so, during the first portion of flight, what's he doing? He's falling and he's speeding up, correct? And what is the net force on him? 50 newtons, due to gravity. Gravity's pulling down the cat with 50 newtons of force, and then he or she, I don't know the gender of the cat, doesn't matter. The cat hits the water, and then what happens? Then we have 50 newtons down and 50 newtons up. And so, Emily, what is the net force? No. The net force is 0. How come? 50 down, 50 up, they're balanced. Net force is 0, which means the object doesn't accelerate anymore, and the velocity stays the same. The pool cover was on. The net force is now 0, which means the acceleration is 0, which means that the velocity is constant. And how do we show constant velocity with a VT graph? With a flat line. Why is it below the axis? Why is the graph below the axis, Karen? Because it's going down, and down is negative. Okay? You should have some sort of description that sort of matches mine over on the right-hand side there. Hopefully you were doing that as I explained it. Right? 50 newtons as he falls, and then once he hits the water, the net force is 0, 50 down, 50 up. Acceleration is 0, velocity is constant, so it's B. Please do not try this with your own cat at home.
Oh, it's okay, I'll try it.
Which one of the following dot diagrams best describes the motion of the falling cat from the time that they are dropped to the time that they hit the bottom of the pool? The arrows on the diagram represent the point at which the cat hits the water. So you probably got this one wrong if you got the first one wrong. Because the cat is speeding up, it's definitely not B, because there the dots are the same distance apart, so it's not B. Here it's speeding up, the dots are getting farther apart, but here they slow down, so the correct answer is, in fact, A. Nobody got that one. We've already established over here, the cat is falling through the water at a constant speed. It's this question. Look, we got a 5 kilogram cat, and the guy's name is Look Out Below. You think this is real life? What actually happens in real life? In real life, the buoyant force is more. That's why the cat slows down. Although, if you throw things in water, they will sink and fall at a constant rate, right? So, I don't know. I think in real life, pretty true. Right? Okay, so the correct answer is indeed A. Okay, last one. Several of Luke's friends were discussing the motion of the falling cat. Being physics types, being students of mine, they began discussing the motion. made the following comments. Indicate whether each of the comments are correct or incorrect to support your answers. Once the cat hits the water, the forces are balanced and the cat will stop. That is false, and many of you said that. Which part is false? The cat will stop. That is false. Is the forces balance true? Yes, it is, but it's an and statement, right? Upon hitting the water, the cat will accelerate upwards because the water applies an upward force. True. There is an acceleration on the cat upwards, right? Number 12, upon hitting the water, the cat will bounce upwards due to the upwards force. No. Right? Forces are balanced. Cats don't bounce off water. Ooh, lots of people said true there. If the force, okay, if you haven't listened to anything at all, this is the number one thing to listen to. If the forces acting upon an object are balanced, then the object A must not be moving, B must be moving with a constant velocity, C must not be accelerating, or D, none of these. The correct answer is, how many got it? Nobody.
D.
Okay, let's go through that again. Let's go through that again. Listen carefully so you get it right. Am I going to ask you this on the test? Is it going to be exactly the same words? No. You're going to have to understand. So listen carefully. If the forces acting upon an object are balanced, so whether it be cats that have 50 newtons down and 50 newtons up, or it could be boxes that have 50 and 50. Does it have to be 50? No, it doesn't. Right? But if the forces are balanced, it must not be moving? No, not true. It could be moving. Can you give me an example where forces are balanced and it continues to move? The cat. The cat is an example column. Driving your car on the highway, right? You still use, when you're on cruise control, you still have gas, you still have that force. You're applying a force against air resistance. The forces are balanced. Things can move when the forces are balanced. They have to move at a, Colin, you're not listening. They have to move at a constant velocity. Okay, so if the objects are balanced, if the forces are balanced, then it must be moving with a constant velocity. I just said that. So maybe it should be B. What if it's not moving at all? Right? What if I push on this big giant desk with, say, I don't know, 10 newtons? It's not moving. How come? Because it's connected to the floor and there's at least 10 newtons of friction. Forces are balanced. Is it moving? It is not. So it must be moving at a constant velocity? No. It could be at rest. Maybe we should jot this in here. Could be at rest. Here it could be. Must not be moving. It could be moving at constant velocity. It could be moving at a constant velocity in A, or it could be at rest in part B. D, none of them. Well, maybe. C must not be accelerating. That is true. That is true. How come? Because when the net force is 0, when the forces are balanced, the net force is 0, therefore the acceleration is 0. Number one thing you need to have learned today.